Hey guys, so we are going to start. So good morning, everyone. Good morning for this June webinar. Today also we will have the last one before the summer break, so it's going to be our last one during 2 months. And today we are here for discussing about the industrial symbiosis, but specifically to the topic of life cycle assessment. So for today we will have here three speakers: Radu Godina, Paul Refalo, and Mehmet Ali Suker. So they are going to do three presentations. One is one life cycle assessment of wire additive manufacturing. Then we will have one related to the using life cycle assessment to decarbonize product and system. And later on, we will have another one regarding linking life cycle assessment and industrial symbiosis for sustainable industry. And finally, after that, there will be some question and answer section, so you could ask whatever you want in the box. I see that you are already asking question. One is just to say good morning, and the other one is to ask about the recording. Yes, I'm sending the recording in an email, and also I provide to you the presentation of today. So don't worry that you will have all the information. Maybe not today because the recording should be uploaded to YouTube channel, but in the coming days. I'm just going, before starting, I would like to do a short introduction of each of our speakers. We will start with Dr. Radu Godina. He's assistant professor at the Department of Mechanical and Industrial Engineering in Portugal, concretely in Nova School of Science and Technology, and also in the University of LIAISE. And he is now he completed in 2016 his PhD and also in industrial engineering and management. He's member of the Directive Council of Udemy Research Center. He also coordinates a master program in maritime logistics, and he has a lot of publications in articles, conference paper, book chapter, editing books, etc. So he has more than around 100 articles, 100 conference papers, and so on. She is publishing in high-impact journals like Clean Air Production or Computer and Industrial Engineering. Later on, we will move for our next one, that is Professor Paul Refalo. He is mechanical engineer and now associated professor in the Department of Industrial and Manufacturing Engineering and the University of Malta. Also, he is associated member of the Institute for Sustainable Energy, also at the university. He has research experience in sustainable manufacture, resource efficiency, and also life cycle engineering. He, apart from participating in different and published in different journals and conferences, he has been part of several research projects. He also supervised undergraduate and postgraduate and doctoral students, and also he has been registered as energy auditor. And finally, we have Dr. Mehmet Ali Suker. He is faculty member and vice chair of the Department of Environmental Engineering at the Izmir Institute of Technology. He has a strong academic and research background in topics like circular economy, waste management, etc. He also has her PhD abroad Turkey in Hamburg University of Technology, and his professional experience includes roles as a researcher but also project manager in different international projects at Germany but also in Turkey. And he also co-founded in 2022 a biotechnology company named Biotech. So in general, his research is focused on energy recovery for waste, sludge management, algal biotechnology, industrial symbiosis, and so on. So that are our three speakers, and now I don't want to take more time to them to make their presentation and their interesting topics. So we will go for the first one, a life cycle assessment of wire additive manufacturing from Radu. So I'm going to start sharing, and I kindly ask you to share your screen when you will be available. As you know, it will be around 12 minutes, so I will just notify you when 1 minute will be missing.
Okay. Good morning, everyone. I'm here to present, first of all, thank you so much for Almudena for making the introduction. I'm going to try to be quite quick and fit into these 12 minutes. I'm going to present, I was challenged to present the life cycle assessment of a specific additive manufacturing process, which is why additive manufacturing. Now, this process was this is in the light of the IT raw materials project called Smart WAAM, which I'm going to use this, which is you can see here. So this project has already finished. It was a European IT project. It was finished last year in July. It was quite successful, and one of the work packages was the life cycle assessment. So without further ado, and I will also at the end I will present a life cycle assessment of one demonstrator which we developed as a output of the project. So really quickly, additive manufacturing, as you know, often also associated with 3D printing or has another names, was one of the most promising manufacturing technology and is loosely associated with Industry 4.0. Now, what happens is this additive manufacturing has some disadvantages, although many of in the literature you can find is quite a lot of benefits, but the disadvantages are not well addressed, or not well addressed, but not as often. So first, the cost of entry is very high. These machines are pretty costly. The production cost as well, additional materials that are needed. It is very slow. So if you want to produce a piece that, let's say it's the size of your smartphone, it will take half an hour to 1 hour at least. And if the piece is, the volume is even higher than that, it will take even way more. And also there's a need for post-processing. You can see that the surface on these pieces are quite rough. They're not that usable, and unless you want to use it as let's say, as a facade element or something aesthetical. Other than that, if you want to be useful, let's say spare part in a machine, then it has to be machined and maybe the surface should be treated depending on the use. This means that it is very slow. So compared with traditional manufacturing, it can produce many pieces per day. This one, it's quite slower. There's also obviously benefits. So you can quite quickly, when you want to develop new products, accelerated prototyping, you can do a lot of customization. There's energy savings, and many in the research, this is what I want to highlight, they addressed environmental benefits. We want to say, okay, so here is to really test this hypothesis. Is actually really more environmentally friendly to produce to additive manufacturing, specifically wide arc additive manufacturing, or not. There's also more like part flexibility, reliability, and supply chain improvements, and also that is it could be questioned, depends on the research. So is this additive manufacturing sustainable? In the literature, you can find is the most likely this answer will be affirmative. However, often not always is the case. So sometimes what can happen is that we need to be careful to actually understand when it is more sustainable. So I'd say yes, in certain cases is, and we need to find out which are those cases. So what additive manufacturing provides opportunities for recyclable materials, lightweighting and reduced waste. To sustainability is much more complex, and we have to verify all the product's entire life cycle. This is exactly what we did, and not only for wide arc additive manufacturing, but as well for other, because you need to compare it with other additive manufacturing processes. So, is it additive manufacturing sustainable? The question is more, the answer is more complex. I would say yes with an asterisk. However, especially in additive manufacturing using all the types of PLA and plastics, There's this eco-responsible 3D printing alliance that has been started in, for example, in UK. And the initiative is to promote sustainable additive manufacturing practices, namely where the product comes from, or sometimes implement biodegradable or recycled elements into the filaments and not be entirely came out of the fossil fuels. So, however, what we associate usually additive manufacturing is to sustainability. But why? And how can a company use additive manufacturing to develop a more sustainable process? So first of all, there's this, we already know all the 17 development goals. And what we have here is this additive manufacturing and the global goals. You can see that there's since from A to H, there's many benefits from that. For example, workers can benefit, training and education, of course, clean production and pollution prevention, with an asterisk, of course, and we'll see that case, quality control and standards. Products performance can be higher depending on the situation, sustainable sourcing, so energy or materials. We should know, trace and know where it comes from, especially now with the digital product passport from EU. Simplified supply chains, especially when you have the machine in-house. So if you need spare parts, instead of ordering them from China, you produce them locally. Although even that, you need to make sure that where the raw material comes from. So where in this case, where the coil will come from for the WAAM. So once we've seen that sustainability is important, how to measure it quantitatively. So we have here, we can see here all the waste that can happen in different situations, and we're well aware of this. And with that, we should use life cycle assessment. But one does not simply, as format shows, do an LCA. It's not as easy as said. So most of you probably know what is, but I'm going to quickly refresh that life cycle assessment is a methodology for assessing not all, but many environmental impacts associated with all the stages of life cycle for commercial use, process, or service. And what it does is a systematic analysis of environmental impact over the course of entire life cycle, models the implications of many interacting systems that make up the industrial production. So when accurately performed, it can provide valuable data for decision making. And we can see that it can start from material production and go through transportation, manufacturing, transport, again, customer use, transport, disposal, or if you want more in a circular economy way, recycling or reuse, and starting from the beginning. So all of that, you need to quantify all the resource extractions in all of these stages and all the emissions that occur in all of these stages. So what we should pay attention is to not to be biased in cases of when you perform life cycle assessment, ignoring, let's say, transportation, or just focusing on a certain part or certain section of the production or all this sequence, and to evaluate the whole chain. So life cycle assessment can be done quickly. For example, just a streamlined life cycle assessment just to check options, or a fast track LCA to identify just what are the highest impacts and establish some baseline. Or you can use ISO 14040, the standard, and EPDs for the United States. In Europe, it's product environmental footprint, PEF. And that will, when you do a full LCA, it takes time. It can take months. So the more into details you go, the more time consuming it is. However, the more increased precision, the better, the more accurate your result will be, and therefore this will result in a better decision making. So you're not ignoring certain elements of the life cycle assessment. So what is life cycles for example? In this case, we have for a 3D printed geopolymer concrete panel. We can see in scenario 1, what happens is, the question is it bad, this result, or good? We have CO2 equivalent, kilograms of CO2 equivalent on the y-axis, and we can see it has all these emissions, almost 3,000 tons. So we're talking 3 tons here. However, is it good or bad? We cannot answer that because we might have an idea, but we cannot answer that because we need it. So the question is it good or bad? We needed to compare. So here we compare it with ordinary concrete panel, and we actually see that the geopolymer concrete panel in the whole has a more negative environmental impact than the ordinary concrete panel. So when you perform an LCA, it should be a comparative contribution of raw materials transport, and in this case, concrete panel manufacturing. And what you see here, for example, that the stage 3, it's the concrete panel manufacturing, it's more damaging to the environment of the ordinary concrete panel, and stage 3 of the 3D geopolymer, it's less. However, if you take the whole chain into account, this first stage, the raw material production or extraction and transportation, then the geopolymer ends up being more negative. So we need to, this is to say that we need to evaluate the whole chain. Now, when you do an LCA, you need to find the scope of the study, so the function, the functional unit, and the reference flow. What are the system boundaries, data categories, quality, critical review, and other applications. Then, if something is not adjusted, you go back with interpretation and you select or add up or remove certain parts. Usually, add up more detail, and then go back and see if the direct application makes sense, or and so on and so forth. So therefore, that's why you do this two-way street interaction between these elements. Now we need to just quickly address what are the boundaries. So some studies for you to understand the ones that are the most I wouldn't say detailed, the most complete are the ones that address the cradle to the grave boundary. This is from the raw material extraction until the disposal or recyclability or reuse. So the cradle when it's born until the grave. When we have the cradle to the gate, it's when it happens when after the manufacturing plant, it is shipped to when it leaves the manufacturing plant, then it stops there. So it's not taking into account what it will emit after, so the transportation, and then especially the customer use. Let's say we produce something, let's say a car, but the customer uses that car for 30 years. That use it's not taken into account if we consider cradle to gate. If we consider gate to grave, it's the opposite. We consider since the customer buys the product until the disposal, and therefore the whole manufacturing part, it's not taken into account. This is sometimes a phenomenon observed when electrical vehicles are analyzed. They're analyzed since the...
Sorry, Radu, 1 more minute, please.
1 more minute, okay. So I'm going to skip over this because we need to address the WAAM with additive manufacturing and in the project. So the additive manufacturing we have here is this. You can see here, this is the machine. And it's basically direct energy deposition, very similar to welding. This is the pieces, how they look like. You deposit one layer each time, and then you have to wait a little bit to cool down. When you produce one piece, it kind of looks like this. Then you need, at the beginning, when I said you need to machine it, and you need to treat it so it will become useful. The comparison was between CNC milling and WAAM. These are the pieces that were built, this one, and this one. So we have geometry 1, 2, and 3. And when they're compared to see not just from one type of geometry, because usually all the studies focus on just a wall, this is more complex pieces. We can see that, for example, the environmental impact is much higher on human health than ecosystem and resources for the geometries. We can also see that CNC milling is much higher than the WAAM. And when compared with the total impact in millipoints, we see that CNC milling has a more negative impact on the environment for all the three geometries, but the geometry 1 is a little bit quite similar. So we can see that there's a difference depending on the type of geometry. Also, the environmental impact divided by the stages of the process. We can see that the steel billet in both cases, especially in both cases now for WAAM, is the one that has the more negative impact. And in the end, the environmental impact between selective laser melting, so SLM, and WAAM, SLM being another additive manufacturing process, it's also more negative. So WAAM has more sustainable potential due to higher build rate and lower energy consumption because this one consumes a lot of energy because it uses laser. This is the piece. You can see that it was then machined after this production. So this is not usable, but after this, and you cut up the base, it becomes usable. This is all the process that was made from the beginning until here. And you can see the end result. And at the end, we also analyze the cost from additive manufacturing WAAM, CNC milling, and laser powder bed fusion. So you can see that, for example, the cost, CNC milling is cheaper if you produce one or two pieces, but with time and the more production volume you have, WAAM then becomes more economical. And also you can see here that in environmental impact, WAAM tends to be less damaging to the environment when compared to laser powder bed fusion and CNC milling. And this is also the costs. The costs show that CNC milling tends to be more economical, but again, this is for one piece. Then you augment the volume, and you can see that the WAAM becomes more economical. And this is one tool came out of this. You can see this if you want to use it, and that's the results. Just to show, just 10 seconds, you put here all the parameters, and then you get the results of the like the type of volume, surface, etc., and you get the results. Therefore, you don't need to have the LCA software. This is online. You can use it. You can play with it, change the type of piece that you want to upload, and it will give you the results of the environmental impact, social impact, and also economical impact. Thank you very much.
Thank you so much, Radu, for your presentation. We will keep the question for the end. So now I would like to give the floor to Paul for his presentation about using life cycle assessment to decarbonize products and systems. So Radu, I think you could share your screen. Sorry, I told you Radu, but Paul, sorry. So Paul, you could just, yeah. Now you could start. Thank you so much. Paul, we are not hearing you. No. Now you are muted. No. I think it's something about your computer because you are not muted most of the time, so. Okay, so Mehmet, if you agree, could you go with you so we allow Paul to repair the problem?
Of course, so if you like, we can continue with me.
Okay, thank you so much. So now we move for the presentation of Mehmet that is about linking life cycle assessment and industrial symbiosis for sustainable industry. So thank you again for reaching the order and for the presentation. The floor is yours.
Okay, so everyone can see my screen as well.
Yes,
Good.
and
Hello, everyone. Greetings from Turkey. So today is the Sacrifice Fest in Turkey. It's a public holiday. So all Muslims celebrate the Sacrifice Fest in all the world. So we will talk about linking life cycle assessment and industrial symbiosis for sustainable industry. So not only the one case, but also the other case can be applied for these method for the synergetic sustainability gains. So as you see in that life cycle assessment, you can see that a standardized science-based method that allows us to quantify the environmental impacts across the entire life cycle assessment products and systems. So it depends on the different signs of international standards, and also industry symbiosis in contrast emphasizes collaboration between industry where waste, energy, and byproducts from one facility are redirected as a source for another. So this approach supports circular economy strategies and enhance the sources efficiency. The objectives here is to show how these two methodologies can be strategically integrated. So today I will show this integration. Why integrate life cycle assessment? So we are witnessing a significant global shift driven by the climate targets, including those outlined in the Paris Agreement, which requires the deep decarbonization across all sectors. So European Green Deal and the Circular Economy Action Plan and waste. So we need some policies and market drivers, so also need for the systematic approach for these integrations. So together they offer a structured way to avoid burden shifting, meaning we don't solve environmental problems in one facilities only to internalize them to another. So instead of we aim for net systematic gains in sustainable across industrial network. So when we look to conceptual symbiosis, so this diagram illustrates how life cycle assessment and industrial symbiosis are not isolated tools, but are deeply embedded within and reinforced by broader policies, industrial and sustainable movement, sustainable development goals, European Green Deals, CEAP, and Fit for 55. So within these, industrial symbiosis plays a central role for these kind of actions all over the world. So to make these synergies scientifically accountable, we integrated life cycle assessment and industrial symbiosis. So life cycle assessments can allow us to quantify the environmental benefit of the symbiosis. So compare it with the baseline system to ensure no burden is shifted as well. So actually, I don't want to give more detailed information. Previous slides, speakers can give the life cycle assessment. So this is a technique for assessing the environmental aspect and potential impact associated with the product, process, or symbiosis. So this is the exchange of materials, energies, water, and byproducts, as well as knowledge among the traditional separate industrial to improve the resource efficiency. So this is a part of circular economy because of eco-industrial parks and frameworks, and also industrial symbiosis as a good beneficial tools for the circular economy as well. So there are four phases of the life cycle process, as you need that. So this is the goal and scope definitions is needed. It becomes with this step followed by the selection of the constitutive functional units. So system boundaries should be identified, and also the allocation methods, either mass-based or system expansion, should be given in this section. Also, The life cycle inventory analysis input and output data are collected for materials, energy and emissions across all facilities is needed. So life cycle impact assessment, impact category modeling should be defined and characterization should be defined in these things. Finally, results and interpretation to identify the environmental hotspots and sensitivity analysis is performed to avoid the uncertainty. So these leads to target recommendation for the optimizing symbiotic flows and minimizations of the system-wide effects as well. So impact categories, when we look the life cycle assessment impact categories of global warming potential, ozone depletion, acidification, eutrophication, human toxicity, abiotic resource depletions, all of them can be defined in the national and international standards, so methods. So it can be really beneficial to categorize the impacts. When we look the industrial symbiosis from isolation to integration, so successful symbiosis relies first on the geographic proximity, which reduces the cost and complexity of the material and energy exchange. So it should be mutual benefit is essential. Infrastructure sharing, trust-based information networks, material reuse, energy integration, water recycling, so and shared logistics. So together, these practice supports the creations of eco-industrial parks and hence the circularity of the regional scales. So when we look the step-by-step methodology for the life cycle assessments of the industrial symbiosis, so you know, the goal of the life cycle is to compare the environmental impacts of the two configurations. So a conventional baseline and an industrial symbiosis integrated system. So depend on this study purposes, either an attributional or consequential modeling approach is selected. Attributional reflects the current average conditions, which consequential assess the effects of the system changes. So functional units should be defined and the functional flows should be defined during this method as well. When you look the system boundaries, in terms of system boundaries, there are three standard boundary system: gate to gate, cradle to gate, cradle to grave. So in this context, industrial symbiosis, the system boundaries must be explained to include the all relevant exchange, not only internal operation, but also the flows, materials, energy, water, and emissions that move between facilities. So next subject is allocating with the multiple outputs is necessary when a process yields, such as a main product and one or more byproducts. So mass balance, economic, and the system expansion or substitutions, which is preferred in industrial symbiosis as well. These methods credit the system for avoiding the production of a conventional product. For the example, when biogas replaced fossil natural gas in terms of this material. So as well as life cycle inventory, so detailed input and output data for each facilities or each symbiotic exchange in the system. So it is also beneficial for the explanation of the system boundaries as well. So data collection is one of the most important point because of we have difficulties in finding the reliable data. So data collection is another important topic. Primary data refers to site-specific information collected directly from the facilities, such as electricity consumption, water use, on-site emissions. This is especially important for accurate modeling system flows between the partners as well. So, and also we focus on the flow diagrams to represent both the baseline and the industrial symbiosis scenarios in crucial. So the objective is to visualize the quantity and direction of the materials, energies, water flows between facilities. So this includes both direct resource exchange and utility level interactions. Examples of the utility exchange include flows of biogas, carbon dioxide, or stream between the facilities. So this is in mapping process is essential to identify the environmental benefits, trace emissions pathways, and to prepare for the impact assessment phase of the life cycle assessment. Also, we use these flow diagrams. So value stream diagrams can be utilized for the lean manufacturing also, as you know. So emission factors serve as quantitative conversion parameters that translate the input and output data. So it is very important. So as you've seen that the interpretations of the results is another part of the life cycle assessments. First, hotspot analysis is performed to identify which processes or exchange are the major contribution to each impact categories. So this helps prioritize the improvement efforts. So we will see the next steps is to compare the baseline and industrial symbiosis scenarios. So also data gaps can be identified in these scenarios as well. Sensitivity and uncertainty analysis component addresses the robustness and reliability of the life cycle assessment results. So a sensitivity analysis is performed by the testing different assumptions such as the alternative allocation methods or variability in the exchange flows. So different kind of goals to evaluate how consistently the industrial symbiosis system outperforms the baseline even under fluctuating conditions. So this is another important point. Also, based on the life cycle assessment results, several design and operational strategies can be recommended to enhance the environmental performance of the industrial symbiosis.
Sorry, Mehmet, one more minute, please.
Yeah, okay. So, enhanced waste utilization, so energy integration or carbon dioxide captures or reuse, also water cascade optimization are the main fundamental tools for the industrial symbiosis as well as the life cycle assessment. So finally, it is important to consider scaling strategies. So either by expanding the symbiotic network or by enabling the policy interventions that incentivize border adaptations. So when we look the integration of life cycle assessment and the industrial symbiosis can be significantly advanced sustainability in the industrial systems. So from a methodological perspective, life cycle assessment provides the scientific rigor. It ensures that the environmental impacts are assessed in a transparent, reproducible, and comparable way for the scenario-based decision making and performance tracking. On the implementation side, the industrial symbiosis enables the systematic restructuring. It reduces the resource input, waste generation, and emissions by connecting facilities through the collaborative exchange. So when these tools are integrated, the benefits are multiple. So integration allows for cross-sectional optimization, quantification, and trade offers the ability to translate the symbiotic opportunities into data-driven sustainability strategies. So as you've seen that how should researchers and practitioners move forward? So for the researchers, I can clearly say that there is a need to develop dynamic life cycle assessment frameworks that reflect the evolving nature of symbiotic networks. So for the industry or planners, life cycle assessment should be used as a decision support tool to prioritize the industrial symbiosis scenarios based on impact reduction potential. So, and this system should promote the development of the open access industrial symbiosis and the life cycle assessment databases to ensure the widespread application and equity in the sustainability planning. So for the integration of these tools is both powerful and necessary. So for the features, maybe quantification through the environmental metrics, but also the practical implementations of the sustainability strategies, these are mutually reinforced. So you can see that the Sustainable Development Goals, SDG 9, SDG 12, SDG 13, mainly supported these tools. So engineers and the scientists must co-develop methodological frameworks. Policymakers must support the integration through the regulations and incentives, and researchers must fill the critical data and the modeling gaps. Thank you very much for all of you joining us during this presentation.
Thank you so much, Mehmet, for the presentation. I see that there are already some questions for you, but let's wait for the presentation of Paul before going for the questions. So once again, thank you. And now let's try Paul. Could you?
Can you hear me now?
Now, yes. Thank you so much. So now, yes, we are going to have the opportunity to have your presentation about the decarbonization products and system using life cycle assessment. So the floor is yours.
Okay. So can you confirm that you're seeing the whole screen?
Yes.
Good. Okay. And apologies for what happened earlier. I can't understand why I was unmuting, but you couldn't hear me. But well, thank you, Almudena, for the invitation to deliver a presentation in this webinar. As you said, I am Paul Refalo from the University of Malta, and I will be presenting how we're using life cycle assessments in our projects, in our research to assess and decarbonize various products and systems that we are working on. Just a brief introduction. When we design for sustainability, right, there are various ways of how we think of what we think of when we design to improve from a sustainability perspective. We design for the three pillars, so we think of the financial, the social, and the environmental pillars. We should be using systems thinking, so we shouldn't be just focusing on one element at a time, but we look at the whole system concurrently. And we should also be using life cycle thinking. So we should be looking into how the products, how the systems, how the processes that we are using would evolve, would go through as they evolve throughout their whole life cycle. So in that sense, we use life cycle thinking for products to see how they go through the different life cycle phases. As the previous speakers already well mentioned, right? Life cycle thinking goes through each and every phase. So raw material extraction, manufacturing, distribution, use, and end of life. Ideally, we design products and systems in a way that they close the loop. Okay, so over here we're in a webinar organized under the cost action targeting industrial symbiosis. So we should be looking into how to close the loop and create a circular economy. Many of the products, many of the systems that we design, unfortunately, end up going to the landfill. So ideally, we see how to close the loop. And life cycle assessments can help us do this, can help us assess and compare, as Radu and Mehmet already highlighted, to compare the various environmental impacts quantitatively over the whole life cycle, depending on the boundaries that we set in our life cycle assessment. And what I'm going to do is, I'm going to show you how we used life cycle assessment in various projects to assess these environmental impacts, starting off with a project which we had in collaboration with a company called Tolly Products. Tolly Products produce packaging systems for makeup brands. So their customers include Dior, Chanel, Sephora, and all those brands. And one of the products which we used as a case study was what you're seeing here on the screen, is a compact for this powder. And Tolly Products asked us to look into various initiatives which they could take to decrease, to minimize their environmental impacts, particularly, obviously, the carbon footprint, the global warming potential. And so we carried out various scenarios to be able to compare with a benchmark, and we compared these various scenarios as I'm going to explain. So we started off with this scenario one, which is the benchmark, but we also considered using different polymers, different plastics. So we started off with ABS, which was their material back then, and we saw if we had to shift to different polymers, what the environmental impact over the whole life cycle would be. So we considered here polypropylene, PET, PLA, and a wood polymer composite. And as you can see, shifting to polypropylene would decrease the carbon footprint over the whole life cycle by more than 50%. However, then they told us, listen, what if we had to shift to renewable energy? What if we had to get 100% energy and 100% renewable energy for our plants? What if we had to decrease the energy consumption in our manufacturing plant by 50%? What if we had to create a circular economy where the customers would simply return the packages, and so those materials could go 100 in the scenario as 100% recycling at end of life. And as you can see, each of these scenarios would decrease the environmental impact by around 10% each. So using renewable energy, although we might think that it is a very good initiative, which mind you, I fully agree, yeah, don't get me wrong, but when we look at it into perspective, when we see it from the whole life cycle perspective, the impact is only of 10%. Reducing the energy consumption in the manufacturing stage by 50% also has an impact of around 10% as well. And same with recycling at end of life. So just recycling the material at end of life would reduce the impact by 10%. So then we looked into further initiatives. We considered dematerializing the design, seeing how to further decrease the material, but not at the expense of quality. Over here, we're speaking of products in the cosmetic business. So quality is a very important factor. And we also then looked into using recycled plastic. So instead of using virgin materials, using recycled plastic. And over here, the impact's decreased by 60 to 70%, depending on the initiative. And then obviously, scenario 7 shows that if we had to do all these initiatives together, the impact would reduce by more than 90%. So these results, although obviously from our perspective, from a scientific perspective, give us good results, but now Tolly, right, know that these initiatives could decrease their carbon footprint, and they also know by how much. And that is a very important tool when it comes to ESG strategies in industry. Another project which we also used the life cycle assessment for was the Microwatts project. The Microwatts project was funded by Interreg, the Interreg Italia-Malta protocol. And over here in this project, we designed a wastewater treatment system which recycles grey water coming from wash hand basins, sinks, showers, baths. Okay, so wastewater coming from personal hygiene, treats it using ultraviolet and photocatalysis, and then uses it as second-class water for toilet flushing. So we had a system which could reduce the water footprint by 30%. Okay, so this is the system which we had designed. Obviously, saving 30% of the water consumption is obviously a good thing. But what we wanted to do was to assess whether this system, using ultraviolet, using all the components, right, all the photocatalytic materials in this case, the pumps, the fittings, and all the resources over the whole life cycle, we wanted to see whether actually this is beneficial from an environmental footprint or not. So again, we carried out a life cycle assessment for the whole, for all the life cycle stages, and we compared the grey water system which we designed with the baseline scenario. So the municipal scenario where we get water, town water, and use it for toilet flushing, and obviously that water goes then to the wastewater treatment plant. So we started off with assessing the carbon footprint for Malta, and I must say over here that we get the majority of our water comes from reverse osmosis. Since our country, Malta, lacks freshwater resources, we rely on around 2/3 of our water coming from energy-intensive reverse osmosis. And so we established that baseline, and we saw that this baseline, the benchmark, the datum, is of around 4 kilograms of CO2 per cubic meter. And then we varied various operational parameters in our developed system, and we varied the number of reactors, the operational time, so how much time it would take to treat the water, and the power of the UV, which we have in the reactors. We varied those parameters, and we saw that there are situations where using the system would in fact not be beneficial. So if these operational parameters result in a carbon footprint which is higher than 4 kilograms, then obviously the water treatment system, it's a water saving system, but it is not environmentally feasible. So in this case, we used life cycle assessment as a design tool to make sure that, listen, if we had to design this system and develop it, we want to have operational parameters which would reduce also not just the water footprint, but the carbon footprint. So in this case, we used this tool to come up with not just a product, with not just a system which saves one resource. Earlier on, I told you that we should be looking at systems holistically, right? Systems thinking and life cycle thinking concurrently. So in this case, life cycle assessment can be used to not just focus on one resource, on one environmental impact, but looking at various environmental impacts concurrently. One last project and system which we also assessed using life cycle assessment was when it comes to compressed air systems. So I don't know how familiar you are with compressed air systems, but compressed air is one of the main utilities which we find in industry, in factories, and it is one of the most also energy intensive processes. So compressed air is widely used in industry mainly for automation and various other processes. However, to add insult to injury, around 30% of this compressed air is lost to leakages, right? So you would have compressors which are just generating compressed air which is lost. And we estimate that these losses in the EU contribute to around 7 million tons of carbon dioxide. So what we did is we used over here national funds coming from Scienza Malta. We partnered with AIM Enterprises, and we also had ST Microelectronics, Tolly again, and Methode Electronics as industrial partners. So what we did, we developed a system which uses industrial Internet of Things and artificial intelligence to autonomously monitor and control compressed air systems. So we came up with a system which identifies and classifies whether you have leaks and tells you how big these leakages are, and then offer an intelligent control system, an intelligent control solution. So not just telling you that you have leaks, but also mitigating the leaks, not at the expense of productivity. So this system works on the demand side of compressed air system, not on the compressor, but on where the demand actually is in real time. And this is what the prototype that we had in the lab actually looks like. So we developed various sensors, various actuators and controllers, which could be used to be able to pinpoint and control leakages in real time. So what did we do? We carried out a life cycle assessment on the extra actuators and sensors which we are using, and we established that, listen, our system generates 500 kilograms of CO2. However, on a system which runs at 7 bar for 10 years, this has the potential to save over 9 tons. So even though it's a system which reduces the energy consumption by 30%, potential reduction of 30%, it has then an environmental payback period of less than 3 months. So in this case, life cycle assessment showed us that it would not just save energy, but in the long term, it would also be environmentally feasible. So I just showed you 3 examples of how we used life cycle assessment in our research, in our design, when we're designing projects, processes and products, mainly targeting SDG goal number 9. Obviously also targeting other goals on water, on energy, and production and others. So obviously, thank you very much for your attention, and I look forward to any questions which you may have. Thank you very much.
Thank you very much, Paul, for your presentation. Quite interesting. I think that there is a question for you. So as you have already the micro on, I'm going to go for you first. The question is, how do you assure the quality of the artificial intelligence and EOT data?
Okay, how to assure the quality of the AI data? So we run various obviously first we have to teach, right, the system. So we carry out various scenarios to create a very robust data set to teach the system of what a health system would be, and then how different faults would affect the system. So we carry out these various runs to be able to create a robust data set, and then we use that data to come up with solutions which would mitigate the fault.
Okay, and for the IoT data, for the Internet of Things, is the same?
Yeah, it's the same data coming
Okay,
from the IoT. So we have various sensors.
perfect. Thank you so much.
You're welcome.
Now I move to Mehmet for the moment. There is a first question for you. Which allocation procedure do you think is more suitable or more robust for more system or products?
So actually, system expansion or substitution for preferred the industry symbiosis because it captured the environmental benefits of displacing conventional products. So, however, mass-based or economic allocation can also be used if system expansion is not feasible. So the choice must be made transparently or consistently. So this is the functional unit maybe should reflect the primary purpose of the iOS, the industrial symbiosis network, allow for pair comparison. So these are the like dynamic network. So it should be flow quantities, exchange partners or market conditions can change. So sensitivity or uncertainty analysis help understood how robust the environmental benefits of the industrial symbiosis are under different scenarios or variations. So they also inform decision makers about the potential risk. So
Okay, thank you so much. And another question for you, it's about reporting. What kind of reporting exists and what do the guidelines recommend?
So reporting one of the most important output because of there's a standard reporting systems for the standardization like 14040. So that kind of standardizations give guideline for the reporting, but results should be reported transparently following the international standard organizations guidelines. So clearly state the functional units and the system boundaries, and also provide the separate results for each impact categories. So report absolute values or relatively comparisons between the baseline and the industrial symbiosis integrated scenarios. So reports should include the hotspot analysis to highlight the key contributions to impacts. So also discussion is one of the most important part of the reporting. So discuss uncertainties, assumptions, and limitations should be commonly include the reporting as well.
Thank you so much, Mehmet. I think you solved both questions perfectly. For the moment, I don't see more questions, so I think also as we are out of time, I would like to thank you to Radu, Paul, and Mehmet for their presentation. I think they are quite interesting and also quite different, so that allows us to have different point of view and different topics to discuss today. So again, thank you for the three of you for your time, especially make that you are in a bank holiday day.
Yeah,
And
thank you.
so thank you so much. And I would like just to mention, say it at the beginning, that will be our last webinar until September, because we are going to close due to the summer period, that and most of you will be or in July or in August in summer vacation. So we come back in September. And regarding this webinar, the recording will be in our YouTube channel, and also you will receive by email the presentation. So once again, thank you also for the audience to be here, and hopefully hope that all of you have a good weekend. Thank you so much.
You're welcome. Thank you. Bye bye.
Thank you very much.
Thank you. Bye-bye.
Bye.
Bye.